In this video, we are going to look at the relationship between work done and energy transferred. Specifically, we're going to look at two things. One would be potential energy and one would be kinetic energy, and sort of the relationship between the two. To begin with, let's talk about biking. Here I've got a bike and I'm riding up a hill. So my question is, if you ride your bike up a long hill, you've expended a certain amount of energy to get up to the top there. But then when you go to ride down the hill, you don't have to expend any energy at all, really, and you just coast. And typically you get going faster. So the question would be, why is that? So why is it that expend a ton of energy to get up to the top, and then you expend no energy and you get going faster down to the bottom? So uh, I guess the idea is that when you lift an object up, like this one, if I bike up this hill to the top, then the position that I'm at with respect to the ground has changed. And what it does is it gives that object and rider energy. And that type of energy is called potential energy. So down here, say I'm talking about relative to the ground. Right now my bike has zero potential energy. But if I'm at the top, then I have a certain amount of potential energy. And you might be able to figure out why you would have that kind of energy or what would make that up. So certainly how high you go up, so the height would have an impact on how much potential energy you have. Maybe how much you weigh would have an impact on the potential energy. And there could be other factors as well. Now, that's not the only way you can get potential energy. You can get it from pulling a swing back or drawing an arrow, and also in chemicals. If you have a certain amount of chemical, like a fuel of some sort, octane, that includes within it potential energy. So a way that you could look at potential energy is it being stored energy. Let's look at some math on how we can calculate that. Here's the formula. Potential energy, so energy with a little p, that's often how potential energy is denoted. Sometimes some people put PE for potential energy. I sort of like using E for energy and P describing what kind of energy, is equal to the product of the mass of an object by the gravity, whatever gravity is, multiplied by the height. Sort of what we were thinking at before. Let's try some questions. Oh, just before we go on, notice that the units for potential energy are joules. Just like we saw earlier in the last video, where the unit for work was also found to be joules. Okay, so let's try a question. A bike weighs 80 kilograms together, go up a hill to a height of 20 meters. What's their potential energy at the top of the hill? Okay, let's figure that out. Potential energy is equal to the mass multiplied by gravity multiplied by the height. So the mass is 80 kilograms. And let me just check back here. Mass, right here, weight in kilograms, good. Heights in meters, and gravity, we always use the same one. Just confirming my units. So 80 kilograms times by gravity, 9.8 meters per second squared, multiplied by the height, 20 meters. I'm going to put a decimal there just to give me two sig figs everywhere. 20 meters. Now I know that when I multiply these out, as long as I have the right units, my answer is going to be in joules. So 80 times 20, 1600 times 10, 16,000-ish. 80, oh, gotta turn the calculator on. 80 times 9.8 times 20 equals 15,680. 15,680 joules of energy. Probably should convert that. We could convert it, but I need two sig figs, so I can only give 15. This is greater than 5, so I'll give it 16. So this would be like 16,000 joules. But you could also convert that to kilojoules. So move it over 3, which is equal to 16 kilojoules of energy. So that's how much energy that biker will have at the top of a 20-meter hill. Stored energy. ready to come downhill. Well, now the question is, what's the minimum amount of energy you need to get them there? If that's how much potential energy they have at the top of the hill, that's how much energy must have been put in order to get you to the top of that hill. Okay? Let's try another question. I have a hawk swoops down and grabs an 800-gram gopher. If the eagle climbs to a height of 250 meters, what's the potential energy of the gopher? Okay, one thing, meters are okay, grams not okay. Got to change that to kilograms. So it'd be 0.800 kilograms. Okay, so potential energy is equal to mass times gravity times height. The mass is 0.800 kilograms. Gravity is 9.8 meters per second squared times the height, 250 meters. Okay, I know that's going to come out to in joules because I've used all the proper units. So 0.800 times 9.8 times 250 meters up, 1960. 1960 joules of energy. That's how much energy, that potential energy, that gopher will have. Let's just look at sig figs again. 3, 3, oh, only 2 for gravity, so I can only give 2 sig figs. So this would be, I would round that up. This is my second one. I have to go here. It's more than 5. This one goes up, so this goes up to 20, and include the last 2 zeros there. Joules, but that's only 1 sig fig. Maybe let's convert this to kilojoules, and that'll help me get 2 sig figs. So it'd be 2.0 kilojoules of energy. That's how much potential energy that gopher has that's up 250 meters. Now, of course, we want the hawk to drop the gopher. That's part of the excitement. So if the hawk were let go of the gopher would lose potential energy as it fell, right? So up here it's got, how much did we say? 20? Whoops. 2,000 or 2 kilojoules of energy. Where am I at? Just a second. So up here I've got 2 kilojoules of energy. As that little gopher got dropped, he would lose potential energy because he's not as high up as he used to be. So where would that difference in the energy go? Well, the difference in the energy, this goes into something known as kinetic energy. And kinetic energy is the energy of motion. If things are moving, they possess kinetic energy. Notice in here, and we'll maybe talk about this later too, but as you would go up, so here's, I've got my gopher right at the top, and it has 2 kilojoules of energy. Say if it drops halfway to the bottom, then in terms of potential energy, it would now only have 1 kilojoule of energy if it drops halfway. So in terms of kinetic energy, if this is my potential energy side, let me erase this one. At the top, it has 2 kilojoules of energy. So at halfway, it would only have 1 kilojoule of energy, of potential energy. But of kinetic energy, it would have 1 kilojoule of energy. Because the addition or the sum of the potential and the kinetic energy always have to be the same number. So at the top there, if the hawk is just stationary, the gopher will have 2 kilojoules of potential energy and 0 kilojoules of kinetic energy because it's not moving, it's just standing still. As soon as it drops the gopher starts gaining kinetic energy and losing potential energy. Let's take a look at a formula for kinetic energy. Kinetic energy is equal to half times the mass times the velocity squared. And this would be the instantaneous velocity. Let's get back to our gopher. So if it's falling and it has an instantaneous velocity of that, notice when that gopher would be falling, back in here, as it's falling, it would get going faster and faster, right? until maybe it reaches that terminal velocity or whatever. But it should get going faster and faster. So we're just going to say at a moment in time, what is its kinetic energy? When it's going 40.5 meters per second. That would be going real fast, actually. So the kinetic energy is equal to a half times the mass times the velocity squared. So a half times the mass, 0.800 kilograms. I've got that in the right unit, kilograms, multiplied by the velocity, 40.5 meters per second, all squared. And this answer will come out in joules, as long as I've used those right units. Let me just check. Velocity is meters per second. That's right. Good. Okay, so formula, a half times 0.8 times 40.5 equals 16.2. 16.2 joules of energy. Let me just come back here. Yeah, that's in joules. So if the gopher was going that fast, that's how many joules of energy it would possess. Okay, now that's sort of a little bit funny compared to this question here, because in this question here, we lifted it to a height of 250 meters. It had 2,000 joules. Oh, okay. So this makes sense, 16.2 joules, a portion of that. It's probably going to be going faster. Okay, so that is the kinetic energy of that gopher. Let's try another question. I've got a 50.8 kilogram person diving from a platform. If they have 10,000 joules of kinetic energy just before entering the water, how fast were they going? Okay, so I have a mass, I have energy, and this is they're moving, so it's kinetic energy. How fast were they going? So it's a simple matter of manipulating my formula. So kinetic energy is equal to half mv squared, and I want to solve for v. So I'm going to take the half and I'll multiply it by 2 on both sides, is equal to mv squared. That got rid of the half. Now I get rid of the mass, so I'll divide. So 2 times kinetic energy divided by the mass will give me velocity squared. And then, of course, we'll do a square root from there. Okay, so 2 times kinetic energy, they say 10,000. Notice it's in joules, so that's good, that's what we're wanting. This is joules. Divided by the mass, the person, how much they weigh? 50.8 kilograms. 50.8 kilograms. Okay, is equal to velocity squared. Let's multiply that out, so it would be 2 times 10,000 divided by 50.8 equals 393.7. 393.7 is equal to velocity squared. Now I need to square root that number. 19.84. 19.84 is equal to my velocity now. And my velocities are always measured in meters per second. Now let's just do sig figs quick. I got 5, I got 3, so I need to go 3 sig figs. So this should be 19.8 meters per second. That's how fast that person would be entering the pool. Okay, now let's do a similar kind of question. So for that last question, the question now is, how high must they have been when they jumped? Well, to figure out how high something is, this formula here doesn't include that, the half mv squared, but this one does. So if they had 10,000 joules of energy when they entered the pool, so just based on that fact that, so here's the diving platform, here's the pool at the bottom, and right here they had 10,000 joules of energy, and that's kinetic energy. If they had that much joules of energy at the bottom, then at the top they would have had 0 joules of kinetic energy. But like we were talking about that logic before, that the sum of kinetic and potential always have to add up to the same, down here at the bottom they would have 0 joules of potential energy, but at the top they must have 10,000 joules of potential energy, because the sum always has to be the same. So I can use this formula here to figure out how high they are, because I know how much joules of energy they had at the top. So potential energy, mass times gravity times the height. This number I know that we're solving for the height, so potential energy divided by the mass and gravity will give me the height. And so 10,000 divided by the mass, how big were they? 50.8. 50.8 times gravity, 9.8. And that's going to give me a height, and my heights are, I know, are always measured in meters. So 10,000 divided by 50.8 divided by 9.8 equals 20. So the height must have been 20 meters. Just looking for sig figs here. I got 3, only 2 for gravity, so we'll give them 2, so it's 20. So 20 meters. So they must have been on the 20-meter platform. Is there one that high? I think so. 10 meter, 20 is up there ways. Anyway, they must have been on the 20-meter platform. So in this video, we've looked at the relationship between potential energy and kinetic energy. Potential energy, energy of stored energy, and kinetic energy, energy of motion. And we've seen examples of using each of those formulas. Try some questions.